All right, let's talk about Riemann sums, which are extremely important in calculus. Let's talk about what they are, what's going on with this section. So suppose you have like a graph like this, okay? You want to find the area between, like, let's say A and B. All right, make this a little thinner. So to find the area between A and B, you would partition the interval up into n little subintervals. So there's n subintervals. So each little subinterval, say that they're even. Well, maybe put one more there. Say they're even. Then we're going to call each one delta x. It's to change in x. Okay. So delta x, that will be the length. It'll be this entire length. So b minus a divided by the number of little intervals you have. So delta x is b minus a divided by n. So then what you do is you decide which side of each little subinterval you want to start with. Let's say we'll start on the right. So here's the first subinterval. So I'll start on the right-hand side of it. And I'm going to make a rectangle that goes up to the graph. And then I go over like that. And then I go to the next subinterval. I go pick the right side. So these will be the right endpoints. Right endpoints. So then I'll go up to the graph and then over. These are supposed to be the same width, by the way. And then I go to the next subinterval. I go up to the graph and then over. And then up to the graph, over, up to the graph and 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 over. Last one, up to the graph and over. And if you notice, there's going to be a lot of little parts in there that are not caught, all right? And that's okay. That's okay. We don't need to worry about that right now. So in order to find the area here, so we're going to find the area under the curve. We add up all the areas of all these little rectangles. Okay, so the area of each rectangle is going to be this delta x piece times the height of the rectangle, each rectangle. And the height of the rectangle is just the actual value of the function at these little x values. So I'm use a different color. So you have an x value here, an x value here, an x value here, 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 and here. So I'm going to call those x sub 1, x sub 2, x sub, make this thinner, x sub 3, x sub 4, x sub 5, and on and on and on. So, for example, the area inside of the last one, let's say the last one here will be 6, 7, 8, 9. 6, 7, 8, 9, x sub 9. The area of the last one, this area inside here, will be f of x sub 9, whatever that is, times delta x. This guy right there is going to go right there. Okay? So, and then the area of the second to last one, that one will be f of x sub 8 times delta x. It's f of x sub 8 and f of x sub 9 because the height of each rectangle is the value of the function. The height of this rectangle is the value of this function. F of x is y. And so if you want to find the height here, that will be the f of x value. This is f of x. So this is f of x, right? All right, so basically you just add all these up. So I've picked a problem that's straight out of the homework. Let's look at it. So if you want to pause the video, you can. So it says, so I've graphed 2x squared minus 9 on Desmos. And we're looking at between 0 and 3. So between 0 and 3 here. So 3 hits up here at 9. Right there, this is 9. All right, so what I want to do is I want to find the area right in here between 0 and 3. Okay, so it says use 6 rectangles. So I'm going to pause the video and make 6 rectangles out of this. Now, we're going to take the midpoints, right? So between 0 and 3. So the midpoints, so let's go ahead and partition 0 to 3 up into 6. So we got this. So it looks like at the half points, we've got it. So this will be at 1/2, and then at 1, and then 3/2, and then at 2, and then at 5/2, and then finally at 3. And now it says take the sample points to be the midpoints. The midpoints. Well, okay, now we got to find the midpoints of all these. So what I'm going to do is I'm going to go off here to the right. Okay, and I'm going to partition this up differently. All right, so what I've done is I've taken this whole thing here and I've translated it there. 0 to 3. Taking my little partitions that I had, and then I'm going to take the midpoints of each because it says midpoints, sample points to be midpoints. So eventually I'm going to be evaluating at these numbers here. These numbers are going to tell me what the height of each rectangle is. So a sample rectangle in this, let's see if I can do this. Okay, so between 1/2 and 0 is 1/4. So we have a rectangle. There's 1/4. Suppose that's just 1/4 right there. Okay, and so the width of the rectangle is going to be like this. And then I'm going to go all the way down. That's going to be the height right there. So the height is where 1/4 is. And so this is the rectangle right here. So I'm going to find this area right here. I could do the same thing between 2 and 3/2. So between 2 and 3/2, 3/2 is 6/4. So this right here is 7/4. Okay, so there's the width right there. And then I go down to the graph and over. So it's going to be a little too much on the right. Okay, so there. So that is going to be my rectangle there. Now, whenever I get to the other side over here, let me make that straight up and down. This is 3. Okay, when I get to the other side, between 5/2 and 3 is 11/4. This is 12/4, right? 3 is 12/4. We have this thinner. In between those two, and so I'm going to go up to the graph, somewhere in there, and then over. This is the width. It's because I'm taking the midpoints. And there we go, like that. Now it turns out that if you had taken the right sides or the left sides, and you find the rectangles that way, the integral answer is going to be very similar. Okay, so what do you do with all this? Well, we're going to add up all these rectangles here, right? So the Riemann sum, the Riemann sum for midpoints will be the sum of all the heights, I, times this delta x from I equal 1 to 6. So it'll be basically, let me write it out and I'll come right back. Okay, so I've started to write them out. So I took the 1/4 there, and finding the height of the rectangle at 1/4, then I multiplied times delta x. Delta x ended up being 1/2. Okay, you do the 3 minus the 0 divided by the number of partitions. Okay, so then I take the second rectangle and multiply times 1/2. That's the height, width, or length and width, whatever. The third one is at 5/4, right? So then do that and times 1/2, height, width. All right, so plus f of 7/4 times 1/2 plus f of 9/4 times a half, and then the last one is plus f of 11/4 times a half, like that. And so when you do all this work, you add all this up. So remember our function here was f of x is 2x squared minus 9, right? So you would do, so first of all, you take out a half, right? All these little halves right here, all these little halves can come out. So take out the half and do f of 1/4, so that'd be 2 times 1/4 quantity squared minus 9. And then, so that's one of them, that's the first one, plus. And now you take the 3/4. So that's 2 times 3/4 quantity squared minus 9 plus, and then the 5/4, 2 times 5/4 quantity squared minus 9. And then you keep going on and on and on. All right. So it turns out the answer is, I think it's like negative 73 over 4 or something, negative 73 over 8. Now, if I gave this to you on a test, I would make it much smaller numbers and it'd be much nicer. Now, the answer ended up, these are your rectangles here. And so the blue graph here is your 2x squared minus 9. And then the midpoint ones. See, look, the midpoint. This is the midpoint of this little interval here. Midpoint of this little interval here. Midpoint. So the midpoints of the intervals are going to determine the height of the rectangles, like that. All right, so that's how you do that kind of problem. The other type of problems are much harder. All right, so this is the problem we're going to do, and we're going to use this theorem to do it. All right, so let's talk about the theorem for just a second and determine what is going on there. So basically it says let me get some white, the integral from a to b of f of x dx. So you have some function, here's a, here's b, and you're finding the area under the graph. It could be below as well, all right? So it could be below as well. Like, just for illustration's point, it's easier if it's positive. All right, so this is equal to, now you take the sum of all the little rectangles, delta x, so you're going to split up, let me write this better, you're going to split up from a to b the interval into n little subintervals, all right? And then you'll, let's say you take the right-hand side of each, so right-hand side of each, and you find that that is going to be the height of each rectangle. So those right-hand sides of each, those will be your little x of i's. So x of 1, and then this will be x of 4, x of 6, things like that. That's that x of I business that's going on right there. All right. Now you allow, there's n subintervals and little subintervals there. So I goes from 1 to n. And then you allow the number of subintervals to go to infinity, because what you want to do is you have some function right here, you see, and you have all your little rectangles underneath, right? Your rectangles underneath. But there's a bunch of gaps in here, right? There's a gap here, there's a gap here, there's a gap here. So then you allow your number of rectangles to get more and more numerous, and all the gaps go away. So you may have n subintervals, say 10 subintervals, then you look at 100, and then 1,000, and then 10,000 subintervals, and eventually the number of rectangles fills it all in. So what you're going to, the way you express that is you say the limit as n goes to infinity in the front right here. So as this guy goes to infinity, the number of rectangles goes to infinity, and then you fill in the entire inside that way. All right. Okay, so delta x is, as before, that is b minus a divided by n. And so let's work this out. So, okay, and then xi, the first xi will be Well, we'll talk about that. We'll talk about that. All right. So let me look at this problem. What do we got? We've got x squared minus 4x plus 8 and 1 to 4. Okay, so I've rewritten the problem and I went ahead and looked at the subinterval. This is between 1 and 4. I just put some hash marks there. That doesn't mean, I don't mean that there should be 1, 2, 3, 4, 5 subintervals. It's just for illustration's sake. All right, so delta x is the width. So that will be the 4 minus 1 divided by n. So the width is going to be 3 over n. So for example, if there is 1, 2, 3, 4, 5 subintervals, then each subinterval will have a width of 3 fifths. 3 fifths, like that. Okay? All right, so we got that. Now, the first little x of I, I'm going to choose the right subinterval, the right endpoints of each subinterval. Okay? So there's not just 5 of them, there's a bunch. You know, there's n of them. But the first one, this is delta x, the first one will be 1 plus, this guy right here will be 1 plus, x sub 1 will be 1 plus delta x, which was 1 plus 3 over n. All right. But there's I of these, so this is the ith one, right? So I want to generalize it, okay? So I'm going to make that 3I over n. So when I is equal to 1, it'll be, so when I is equal to 1, it'll be 1 plus 3 over n. When I is equal to 2, it'll be 1 plus 6 over n. This is I equals 1, I equals 2, I equals 3. So the I will change, okay? So the little x sub i's are going to be this. So that's what's going to go in this little formula right there. So let's write that out. So I'm not going to do the limit just yet. I'm going to tack on the limit at the end. So we have sum f of xi delta x I equal 1 to n. So this is sum of, let's see, this is f of 1 plus 3I over n. This is I equal 1 to n. And then the delta x, that was just found to be 3 over n, right? So this is 3 over n. Okay, now we evaluate what f of that is. So this here, inside the integrand, that is f of x. So this is going to be sum I equal 1 to n of, now we're going to put x squared in. So 1 plus 3I over n squared minus 4 times 1 plus 3I over n, and then plus 8. So this is the x squared minus 4x plus 8. And now, you know from your pre-algebra class that you can split this summation up. This is I equal 1 to n of, and I'll write it. So what I did was I multiplied this out right here, and that is right here. Just FOIL it out. Multiply the negative 4 through. That is here, there, and then the 8 just comes for free. So I have that, and now I'm going to combine terms, which I did right here, and now I can split this up. See that the variable here is I. The only thing that's changing is I, right? Not n. So anything that doesn't have an I in it can come out. So this is 9 over n squared, sum I squared, minus 6 over n, sum I, plus sum 5. It's all I equal 1 to n, right? I equal 1 to n. I equal 1 to n. All right, so see, n's not changing in this. The only time that n is going to be changing is when we go way up here and we finally take the limit, okay? But it's not changing just yet. Only I is changing in these summations. Try to work that out in your head for, you know. Okay, so now we know from pre-calculus that there are formulas for these. And these are in the book. I don't know what page it is. It's 5.2. These are in the book. But let me, they're like this. Let me show you a little bit. I'll try to cut and paste one and pull it back. Okay, let me just refresh your memory a little bit on this. If you this formula here works because if you take let's say sum I equal 1 to 4 of I squared. So that would be 1 squared plus 2 squared plus 3 squared plus 4 squared, which would be 1 plus 4 plus 9 plus 16. So that would be 30. Okay, so now I'm going to take the other side and I'm going to evaluate it that way instead. So n is 4, so it would be 4 times 5 times 9 over 6. So this cancels. This is a 2 and this is a 3. This is a 3. This is gone. So this is 2 times 3 times 5, which is 30. So you get the same exact answer. So anywhere I see an I squared, so my I squared, I can put this right-hand side instead. So basically, that's what I'm going to do here. So we get 9 over n squared times, and then n times n plus 1 times 2n plus 1 all over 6, and then minus 6 over n. And then the summation of I, you see that from the book, that one is n times n plus 1. All right, that's the top one there. And so that'll be times n plus 1 all over 2. And then this, if you have a constant, it's just 5 times n right there. All right, so that gets rid of the sigma notation. And now you just clean it up. All right, so I'm going to clean this up. All right, so I cleaned it up. A little bit of algebra going on here. Now, so this here is just the f of xi piece, okay? We have to go back and pick up that 3 over n that is in here, okay? So all I've done is, let me erase some of this. All I've done is I've taken care of this piece here, and that goes all right here. But this 3 over n never came with it. So what I'm going to do is I'm going to multiply by 3 over n down here. So all this is going to be multiplied by 3 over n. All right. So now what we get is 9 over 2n plus 9 over 2n squared plus 15. The n's cancel on the last one. And now we apply that limit. Where's the limit? Limit. Now so now we have done all of, this is I equal 1 to n. We've done all of this. And now we apply the limit. Apply the limit so that integral from 1 to 4 of 2x squared minus 9 dx is equal to the limit as n goes to infinity of all of this. All of this goes inside here. And as n goes to infinity, the first one goes to 0, the second one goes to 0, and the last one just goes to 15. And that's the answer. And that's how you do these. I'm sorry, 2x squared minus 9 was a different problem. This was x squared minus 4x plus 8. All right, so yeah, there we go.